Section 5.1, again, area of a general region. Now today, I want to show you more examples about this topic. Take a review first. Number 1, find the area of the region bounded by a curve and the x-axis and between A and B. There are 4 steps. Here, I draw a diagram about the region S. Okay, S. S, this region, lies between this curve and x-axis and between A and B. And I want to find the area of the region S. There are 4 steps. Step 1, evenly cut the interval AB into subintervals. Here, I have cut the interval AB into n subintervals. And the cutting points, I name the cutting points by x0, x1, x2, x3, and so on. Usually, x0 is the left end point of the interval AB. And the last cutting point, xn, usually is the right end point of the interval AB. Because I cut the interval AB evenly, so each subinterval has the same length. And the length of each subinterval usually is denoted by delta x. Delta x is computable. From A to B, the length is B minus A. Now B minus A is cut into n parts. So each part, the length is B minus A divided by n. This is the length of each subinterval. Now we have subintervals. Over each subinterval, build one rectangle. This is step 2. On the first subinterval, arbitrarily pick a point, x1 star. Usually, this point is the left end point or the right end point or the midpoint of the subinterval. But it can be any other point, okay, in the first subinterval. Okay, now I use the function value at x1 star as the height to build one rectangle. Over the second subinterval, arbitrarily pick a point, x2 star. Again, this point usually is left end point, right end point, or the midpoint of the second subinterval, but it can be any other point. Now use the function value at x2 star as the height to build one rectangle. Do the same for the remaining subintervals, build rectangles. Now step 3. Compute the area of each subinterval, then make a sum of all the areas. The first rectangle, the area is base times height. Base, delta x, height, function value at x1 star. Base times height. So this number is the area of the first rectangle. Area of the second rectangle is base times height. Base, again, delta x, height, function value at x2 star. So compute area of each rectangle, then make a sum of the areas. Now, from this diagram, we can see that the sum of the areas of all the rectangles roughly is the area of the region S. Yeah, roughly. A here, I mean the area of the region S. A is about this sum. When n is larger, what is n? N is the number of rectangles. When you use more rectangles to approximate the region S, then this approximation is better, more accurate. More rectangles, then the approximation is more accurate. The approximation to the region is more accurate. So the area of the region, the area A of the region S is better approximate by this sum as n increases. Now, step 4. To make this approximation into an equation, we need to take limit. We need to increase the number of the rectangles to infinity. Then the sum of the areas of the rectangles will approach some number. The number is A, exactly A, the area of the region S. So take limit, then the area of the region is equal to the limit as n approaches infinity. This is a review of the 4 steps to compute the area of a general region. Now, review number 2. A, this letter contains only a little information. A, what is A? A just means area. Okay. Instead of using A, we usually use this integral notation to denote the area of the region S. This integral notation, as we have seen in the last class, it contains information about the 4 steps. Okay, now usually we don't use A, but use this integral notation to denote this limit. So integral is this limit. This equation is considered to be the definition of the integral. This integral. Yeah. What is an integral? Integral means the limit of the sum of areas of rectangles. We know that a limit may or may not exist, right? When there are more than one limit, then the limit doesn't exist, right? When the limit exists, we say that the function f is integrable. If the limit doesn't exist, then we say that the function is not integrable from A to B. Yeah, when the limit exists, we say that this function is integrable from A to B. Otherwise, no, not integrable from A to B. Yeah. Let's look at some examples. Example 1. Complete the following steps for the following function, interval, and the value of n. N here is the number of rectangles. Its value in this example is 6. That means that we need to use 6 rectangles to approximate the region that lies between this curve and the x-axis and on this interval. To build rectangles, we need to cut this interval into 6 subintervals. Now, the first question. Calculate the length of each subinterval and tell the grid points. Here, grid points means the cutting points. The cutting points. Now let me answer question A first. The length of each subinterval by formula, it is b minus a over n. Now b is 4, a is 1, n is 6. So delta x is 0.5. That is, when we cut this interval evenly into 6 subintervals, each subinterval, the length is 0.5. Now, tell the grid points, tell the cutting points. X0 is always the left endpoint of the interval. So X0 is 1. The cutting point that follows X0 is X1. X1 is 1.5 because the length of the subinterval is 0.5. So X1 is 1.5. The next cutting point is X2 is 2, and so on. X6 is the last cutting point. The last cutting point is always the right endpoint of the interval. So X6 is 4. So in total, 7 cutting points. B, illustrate the left, right, and the midpoint Riemann sums by sketching the appropriate rectangles. Then determine which Riemann sum underestimates and which sum overestimates the area under the curve. Okay, here we have 3 figures. The first figure is about left Riemann sum. I cut the interval 1, 4 into 6 subintervals. Then over each subinterval, I build 1 rectangle. But the height, over the first subinterval, I use function value at the left endpoint of the subinterval as height to build 1 rectangle. Over the second subinterval, I use function value at the left endpoint. Left endpoint is x1 as the height to build a rectangle. Over the third subinterval, I use function value at the left endpoint x2 as height to build a rectangle, and so on. The sum of the areas of these 6 rectangles is the left Riemann sum. The notation is L6. L means use function value at left endpoints to build rectangles. 6 is the number of the rectangles. From this diagram, the region S is the region under the curve. The region S contains all the 6 rectangles. Therefore, the area of the region S is greater than the sum of the areas of these 6 rectangles. So the left Riemann sum is underestimates the area of the region S because L6, the sum of the areas of these rectangles is less than the area of the region S. So L6 underestimates the area of S. This second figure is about right Riemann sum. Okay, cut interval 1, 4 into 6 subintervals. Over the first subinterval, I use function value at the right endpoint. Right endpoint is x1 to build a rectangle. over the second subinterval, I use function value at the right endpoint x2 as height to build a rectangle, and so on. The sum of the areas of these 6 rectangles is the right Riemann sum. The rotation is R6. Again, R means use function values at right endpoints to build rectangles. From this diagram, now this time, the region S is contained by the 6 rectangles. So area of the region is less than the sum of the areas of the 6 rectangles. Therefore, this time, the right Riemann sum overestimates the area of S, of the region S. Now, the third figure is about midpoint Riemann sum. Cut interval 1, 4 into 6 subintervals, build rectangles. Over the first subinterval, I pick midpoint. Because the first subinterval, left endpoint is x0, right endpoint is x1. So I use this notation, x 0.5 to denote the midpoint. Then what is the value of x 0.5? What is the value of the midpoint? Left endpoint x0 is 1. Right endpoint x1 is 1.5. So the midpoint is 1.25. So the value of this notation is 1.25. Use function value at this point as height to build a rectangle. Similarly, over the second subinterval, left endpoint is x1, right endpoint is x2, the rotation. So the midpoint, I use x 1.5 to denote the midpoint of the second subinterval. Then what is the value of this rotation, x 1.5? Left endpoint, the value is 1.5. Right endpoint, the value is 2. So the midpoint, the value is 1.75. So this guy, its value is 1.75. Now, function value at the midpoint as height to build a rectangle. Over the third subinterval, left endpoint, the rotation is x2. Right endpoint, the rotation is x3. So the rotation for the midpoint makes sense to use x 2.5 to denote the midpoint of the third rectangle. Then what is the value of x 2.5? Left endpoint here, the value is 2. Right endpoint, the value is 2.5. So the midpoint is 2.25. Yeah, the value of this guy is 2.25. Now, function value at this point as the height to build a rectangle. And so on, okay? Build rectangles over each subintervals, okay? Now, the sum of the areas of these 6 rectangles is the midpoint Riemann sum. The rotation is m. M means midpoint, 6. Yeah. Now this time, from this diagram, I cannot tell, okay, area of the region S and the sum of the areas of these 6 rectangles, which one is larger, which one is smaller. I cannot tell this time. So I cannot say that M6 is overestimate or underestimate the area of the region S. No answer, no conclusion. Yeah. Now, part C. Calculate the left, right, and midpoint Riemann sums. Okay, let me compute the left Riemann sum first. It is the sum of the areas of 6 rectangles. The first rectangle is on the first interval. First subinterval is left endpoint is x0. So base times function value at x0. Function value at x0 is the height of the rectangle. Base times height, area of the first rectangle. Second rectangle is on the second subinterval. Second subinterval, left endpoint is x1. So the height of the second rectangle is function value at x1. So base times height, area of the second rectangle, and so on, so on. Delta x is common to all the terms, so I factor delta x out to get this equation. Now plug in the function f. What is the function f? Let me see. Function f is e to x over 2. So function value at x0 is e to x0 over 2. Function value at x1 is e to x1 over 2, and so on. Now plug in the values for delta x for the cutting points. Then we get this equation. Value for delta x is 0.5. x0, the value is 1. x1, 1.5. x2, 2. Then calculator, then we get L6 is this number. Now next, let me compute the right Riemann sum. Right Riemann sum is the sum of the areas of 6 rectangles. The first rectangle is on the first subinterval. The right endpoint of first subinterval is x1. So function value at x1 is the height of the first rectangle. Base times height, area. Second rectangle is on the second subinterval. Second subinterval, the right endpoint is x2. So function value at x2 is the height of the second rectangle. Base times height, area of the second rectangle, and so on. Again, factor delta x out to get this equation. Then plug in the function to get this equation. Then plug in the values for delta x for x1, x2, x3 to get this equation. Finally, calculator to get R6 is this number. Do the same for the midpoint Riemann sum. Midpoint Riemann sum is the sum of the areas of 6 rectangles. Those rectangles were built by using function value at midpoints. This is the area of the first rectangle. Base times function value at the midpoint of the first subinterval. And second rectangle area is base times height. Height is function value at the midpoint of the second subinterval, and so on. Factor delta x out, then plug in the function, then plug in the values for the midpoints and for delta x. Finally, calculator to get M6. Example 2. Let A be the area of the region that lies under the graph of this function and between 0 and 2. Question A. Sketch the graph of the function between 0 and 2. B. Using right endpoints, find an expression for A as a limit. That means that write the area A as the limit of the sum of areas of the rectangles. Those rectangles should be built by using function values at the right endpoints of the subintervals as height. Don't evaluate the limit. Maybe the resulting limit is too difficult to evaluate by hand. So don't evaluate the limit. Okay, now let me answer the two questions. Question A, sketch the graph of the function here. This curve is the graph of the given function. The curve is a decreasing curve. Now B, using right endpoints, find an expression for A as a limit. So I follow the 4 steps in the review at the beginning of today's class. Okay, follow the 4 steps. The interval is 0 to 2. Now I evenly cut the interval into n subintervals. Cut, okay. The cutting points are x0, x1, x2, x3, and so on. The length of each subinterval is, by formula, delta x, the length of each subinterval is b minus a over n. Now b is 2, a is 0. So the length of each subinterval is 2 over n. The values for the cutting points are x0. x0 is always the left endpoint of the interval. Now the interval is 0 to 2, so x0 is 0. Now x1, okay, this distance is delta x, so x1 is delta x. Delta x is 2 over n, so x1 is 2 over n. x2, from 0 to x2, the distance is 2 delta x, so x2 is 2 delta x. So it is 2 times 2 over n, 2 times 2 over n. x3, similarly, x3 is 3 delta x from the origin, so x3 is 3 times delta x. So it is this number. Plug in 2 over n in delta x. So 3 times delta x is this number. The last point here, it is n times delta x, the distance from 0. So xn is n times delta x. Delta x is 2 over n, so we get this number. This number, if we cancel n, it is 2. So xn is 2. So the last point is always the right end point of the interval. Right end point of the intervals. This is 2. Yeah. Okay. Now we have subintervals. Now build rectangles. Over the subinterval, use function value at the right endpoint to build a rectangle. Over the second subinterval, use function value at the right endpoint to build a rectangle, and so on. Now, area of the first rectangle is base delta x times height. Area of the second rectangle is base times height. Area of the third rectangle is base times height, and so on. Yeah, this is the sum of the areas of the rectangles. This is the right-Riemann sum. Yeah, this sum is the right-Riemann sum because the rectangles are built by right endpoints. Now, factor delta x out, then we get this equation. Then plug in the function. What is the function? Function is e to negative x. So function value at x1 is e to negative x1. Function value at x2, e to negative x2, and so on. Delta x is n, is 2 over n. 2 over n. Now, the values for the cutting points, plug in the values in the cutting points. x1 is 2 over n, so plug in 2 over n in x1 to get this term. x2 is this number. Plug in this number in x2 to get the second term, and the third term, and the last term, and so on. Okay, now area of the region. Area of the region is the limit of this sum as n, the number of the rectangles approach infinity. So area is the limit as n approaches infinity. It's the limit of the right Riemann sum as n approaches infinity. So plug in this sum in Rn, then we get this equation. This is the answer to this example. This limit by hand, impossible to get it. Then how to get this limit? You need to use a computer to get this limit if you want to find the limit. The following two examples are about the sigma notation. Example number 3. Expand this sum. This sum is written in sigma notation. K is a variable. K can change from 1 to 5. From 1 to 5, there are 5 numbers. So this sum has 5 terms. When k is 1, plug in 1 in k, then we get first term. Plug in 2, k is 2, plug in 2 in k, then we get second term. K is 3, the third term. K is 4, the fourth term. K is 5, the fifth term. So this sigma notation is this sum. Now, example number 4. Example number 4 is a reverse process. We have 2 long sums. Now, can you write each of these 2 long sums into a sum in sigma notation? Okay, A first. This is a long sum. Now, to write this sum into a sum in sigma notation, you need to determine one pattern among the terms. Okay, now let me try to figure out the pattern among the terms. I can write the number 3. Okay, 3 and 8, the difference is 5. So let me write 3 as 3 plus 5 times 0. And write 8 as 3 plus 5 times 1. Similarly, write 13 as 3 plus 5 times 2. Okay. And so on. And 63 is 3 times 5 times 12. So in total, how many terms? From 0, 1, 2 to 12, in total there were 13 terms. Okay. Now, the general term is 3 plus 5 times k. What is k? When k is 0, first term. When k is 1, second term. When k is 12, the last term. So this long sum is summation sigma notation, summation of the general term with k going from 0 to 12. This is the answer. Now the second long sum, okay, second long sum. Okay, again, let me figure out the pattern among the terms or in this long sum. The first term, how about let me write the first term as, write the 2 in the first term as 1 plus 1. Second term, how about let me write the number 3 as 2 plus 1. Third term, write the 4 as 3 plus 1, and so on. The last term, write 50 as 49 plus 1. So then, can you see the pattern? The first term is 1 plus 1. Second term, 2 plus 1. 2 times 2 plus 1. Third term, 3 times 3 plus 1. So the kth term is k 1 over k times k plus 1. When k is 1, then this is first term. When k is 2, this is second term. So this long sum is summation of the general term with k going from 1 to 49. When k is 49, last term. Example number 5. This is the last example today. Okay. Fill in the blanks. Okay. Yeah. Here, blanks. What is this number? What is this number? What is this number? Okay. Fill in the blanks. We have a sum. This sum is a midpoint Riemann sum for function f over some interval with n. This n is the number of rectangles. Okay, first, let me expand this sum. Okay, expand this sum. When this sum has 4 terms, from 1 to 4, 4 numbers, so 4 terms. When k is 1, then I get first term. When k is 2, f of 1.5 plus 2, then I get second term. When k is 3, third term. K is 4, fourth term. Now, 1.5 plus 1 is 2.5. 1.5 plus 2 is 3.5, and so on. So this sum in sigma notation is the sum of these 4 terms. Okay, each term is area of a rectangle. So how many rectangles? 4 rectangles. So n is 4. So n is 4. N means the number of rectangles. N is 4. Then what is the length of the subinterval? Length of subinterval is here. Is here. So delta x is 1. Delta x is 1. Okay, now how to determine the interval AB? So here, AB here, AB here. Now cut this interval evenly, cut into 4 subintervals. Cut, 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 cut into 4 subintervals. And this sum is midpoint Riemann sum. That means that 2.5 is the midpoint of the first subinterval. 3.5 is the midpoint of the second subinterval. The third subinterval, the midpoint is 4.5. And the last subinterval, midpoint is 5.5. Now, each subinterval, the length is 1. And midpoint, below midpoints, and below the length of each subinterval. Then, what is A? What is B? Okay. From here, from this point to this point, the length is 1. The midpoint is 2.5. So what is A? A should be 2. And this point is number 3. Then similarly, how to tell B? From here, from this point to B, the length is 1. The midpoint is 5.5. Then what is B? B is 6. So the interval is 2 to 6. Therefore, this is a midpoint Riemann sum for function f. I don't know what the function is. Okay, on the interval 2 to 6 with the number of rectangles 4.